Right. So thank you for the invitation, and thank you for being here with me today. It's really, I'm impressed by the diversity and the range of the topics that has been covered here, from computational, synthetic, and environmental remediation of, and more topics like new synthesis, new catalyst. So as he mentioned, and then as the first slide shows, we're coming from a community college. So as most of you know, community colleges, they are mostly focused on teaching, but there is a new trend in community college that they are trying to foster science research. So now is one of the requirements for tenure is that you have to have a certain number of publications. So it's now the title of community college is kind of growing. So this is part of the results that is coming out from that, new vision that we have for community college. Okay, so what we're trying to do is, we're going to show you today are the results that has been, worked during the last 2 years. I've been, as a full-time for the last, this is my 3rd year, so here we're focusing on heavy metals. So we have really been covering many type of pollutants. So we started with heavy metals because those are kind of, they're still one of the most important pollutants that is a huge concern. Later on, I will show you how we are taking care of some emerging pollutants like antibiotics, and also right now we're also just trying to see how we can clean phenolic compounds, moving more towards the organic side. But what we're going to show you first is the heavy metals, which are our preliminary data that we got from the beginning. So what is wrong with heavy metals? That's widely known, right? So we know that the toxicity of heavy metals is silent. So we can be drinking something with a huge amount of heavy metals, and we are not even noticing. So that's the problem. It replaces some other ions like calcium, potassium, and then it kind of they definitely diffuse any enzymatic activity, and then they have a toxic effect. So what are we doing about that? I mean, there are many type of technologies that are taking care of the cleaning of the water. So we have reverse osmosis, you have the uses of adsorbents, you have electrodeposition, you have chemical precipitation, but bioremediation is using organic, biological materials to do this removal. So some of them we can use living organisms, and you can use dead organisms. So for living organisms, here is a picture that you can see how the cells are in the first stage, and then they start eating the pollutant, and then they kind of encapsulate them inside until they reach like a toxic level, and then the bacteria cannot take more. And on the other side, we have dead materials, dead biomass. For example, eggshells that they have no use at all. So after once we're done with the eggshells, they go to the trash, and then they just go to the landfill and to other destinations. So in our case, biosorption, we are emphasizing biosorption. Bioaccumulation, there's nothing wrong with it. It's more specific, it's more selective, but it has the problem that you have to give the proper temperature, you have to feed the bacteria, you have to keep it stirring, you have to provide oxygen. So it's kind of a little bit more complex to take care of bioaccumulation, because you are dealing with a living organism and you don't want to upset your bacteria. So in biosorption, what we are using is everything is dead, so you have a passive removal of the pollutants. It's only driven by physical chemical processes, as is coming in the next slide. We have the steps or the mechanism how you can do the adsorption, and then we have series of materials that we have been using, but we are emphasizing today in Tealeafs, and then Tealeafs also are the ones that we're going to be using as a scaffold for chemical modification, which is the goal of our project. The advantage of biosorption is they have a fast kinetics, so it's in less than an hour you can take. In most of the cases, you have half an hour, 25 minutes that take most of the, all the pollutants, and then you can recycle waste. So Tealeafs, we get it in a massive amount from industries. So here, this slide is presenting all the mechanisms, we're very familiar with most of this. So ion exchange is one of the most important. What you are doing is just replacing one ion by your pollutant. And that is because of the acidity, the Lewis acidity of the heavy metals, this process is enhanced. So you are replacing sodium, potassium, and calcium by more toxic metals like lead, copper, cobalt, or mercury. There is some other mechanisms, precipitation, which you don't want. I mean, you might have some precipitation on the surface of the pollutant, but you know, as it's precipitating, it might escape of the surface. So we're really striving for the ion exchange methodology. What are the advantages of biosorption? We have competitive performance. So what we're doing is, why don't we go to these industries, Arizona, Neste, Snapple? They produce every day tons and tons of tea. What do they do with the tea leaf? What do they do with the cellulose? Landfill, landfill, landfill. There is no other use for those tea leaves. So why don't we talk to these guys, take these tea leaves, they come in a proper size. We don't have to grind it. We don't have to, you know, chop it or anything. It comes in the proper size. So we take it and then we make these large filters that are, the selectivity is kind of comparable to the normally, you know, commonly used materials. There is a selectivity. So as I will show later, we put the pollutant in with salt, for example, seawater, sodium chloride, sodium nitrate, and calcium nitrate, and then your pollutant is going to say, I'm going to take your heavy metal. I don't care about the salt. So that's an advantage. Why? Because in case that you have a spill in salt water or in an ocean, so you can definitely target your pollutants that way. It's cost effective because, again, we're taking waste, right, to remove another type of waste. We have pollutant recovery. Normally we don't want to recover pollutant, but how about if we think of gold or we think of silver or some other precious metals? So what you want normally, those runoffs, the residual waters of these industries, they contain small amounts of gold and silver, and I'm pretty sure that these industries are going to be very interested in recovering that small amount of gold and silver for, you know, to continue with the business. There is no sludge generation because we are not forming any cake. There is no filtration. There is no, I mean, there is the precipitation like a sludge that you're forming after the process. Okay, so here there's another type of adsorbent that we are generating. These are hydrogens, are alginate. They've been used for encapsulation for biomimetics, but in this case we're using it for also as a decontamination. Why? Because these gels are formed by the interaction with calcium. As we said before, calcium likes to be replaced. So you have a pollutant and then calcium is going to do the exchange with the heavy metal. That's the type of mechanism. It's pretty simple. It's a peristaltic pump, and then you just pump in the sodium alginate into a solution of calcium chloride, and then you get a perfect bead that is highly porous, and then you're able to encapsulate things inside. Okay, so the methodology for the tea leaves we're boiling. Maybe our lab is the most relaxed lab because it's always smelling like tea. We're preparing peppermint, green tea, chamomile, chai tea. All those teas are being boiled every day to prepare our adsorbents. Of course, this is in the small scale, but that's really not our idea in the long term. What we really want is to target these industries, these big industries, to get their waste. So we optimize different types of parameters, equilibrium parameters like pH, mass. We want to know what are the optimum conditions that are going to make our process, you know, optimum and then, you know, competitive with the currently available methodologies. So we use to characterize the materials because we also want to know what makes it so special. So what is inside of these materials that is making it so attractive to pollutants. So these are the methodologies that we went through, and as we will be digesting it little by little. Our methodology, how to do the quantification, is color-based. Again, so in a community college, we are always, you know, kind of connecting the educational part with the research. So anything that is color-based, as long as it's giving you the detection limits that are reasonable, right? So the limits that are helping you for your quantification. So color-based are perfect, you know, perfect thing, for the students to identify. So this is the quantification. It's a reaction with silicon. It's a complex that you form with the heavy metals. And then here are our adsorbents after the adsorption. So you see the beads are here completely clear, and then that's after the adsorption of copper. And then here you have after the absorption of cobalt. So you have that the heavy metals actually being taken by these materials. So for the results, the first is the characterization. So here we have a TGA. TGA is for material science. It's a technique that will allow you to know how resistant is your material as you change the temperature. We don't want a flammable. You don't want to have a material that is just going to melt during the industrial process, right? In the case that you want to kind of scale up your methodology. So here, from this graph, we can see that our adsorbents are resistant up to between 250 and 300 degrees, which is a very optimum temperature for materials to be stable. So after that, you start losing some organic mass. But up to that, so it's pretty stable. This drop is for moisture. So the first one, the initial, is moisture. It's just the humidity that is inside. So we also did a quantification of the surface area and porosity. So they're very, they change. It depends on the type of leaf, right? Each leaf has a treatment. For example, chai tea is a mixture of herbs. So you have cinnamon, cloves, you have tea, black tea, white tea. So there are different types of substances inside, herbs inside. So, but the ones that we're really targeting is peppermint, green tea, and chamomile, because they come as pure samples. Okay. So here is the scanning electron microscope. So this is it's a huge magnifier. So all what we wanted to see here, that's natural to see in leaves, but we just wanted to confirm is that our surface has pores, has holes where our pollutant can be trapped. We don't want a smooth and shallow surface, because if you have a smooth surface, the pollutant is just going to go on top and then it's just going to fly away immediately. So we want to have like like galleries and caves inside where they can be housed. So these are the other adsorbents. Of course, FTIR to characterize what are the functional groups that are present in our adsorbents. So we have carbonyl, carbonyl here, hydroxyl groups. Those are the groups that are most important. They're commonly identified in this for these materials, as is logical, right? Because we have polysaccharides mostly. This is the X-ray EDS adsorption spectrum. So what we were trying to do here is just to confirm, do you really have your pollutant on the adsorbent? Didn't it precipitate, or it maybe form like a colloid or something? No, here is the proof that we have peppermint, all the elements, and then here with cobalt we see a new signal of cobalt here for the sample after adsorption, and then for copper we have one signal here and then a second signal in here. So the pollutant is actually inside of the adsorbent, so there is no really a false positive result. So we were trying to optimize the process. We tried to change all the parameters. pH was one of them. So it's the most important, because you want to know, can we apply this to natural water, right? Or any residual water that is normally what you are targeting is a pH between 6, 7, 8. Let's say that's the range. So then our results are showing that our adsorbents can be definitely used in that range with the highest removal. Then it's a mass effect. We were trying to change the mass, because in the industry, of course, it's going to be really useful to know. I don't want to waste 1 kilogram if I'm going to get the same result with 1 gram. So that's the curve. So we were changing different masses to optimize, what is the minimum mass that will take you to the maximum adsorption. The same thing we did with concentration. With concentration, what we wanted to know is, can you feed your adsorbent? It's not something that you can do forever. At some point, the adsorption is going to stop because you're going to saturate your adsorbent. So that's the limit that we wanted to know with these materials. So that will take us to isotherms. So that's the modeling part that you obtain the maximum adsorption capacity of each of your adsorbent. That's kind of like a rule to compare all your your adsorbent. For example, you want to compare that with activated carbon. The first thing you do is, oh, what is your Qmax? That's normally the language that we use in adsorption. So salinity, that's the effect that we were talking about before, right? So we wanted to see what is if it affects or not the adsorption, and then it has a negative effect, but you still have some adsorption. So here we were going to, extreme condition with calcium, but it decreases it, but you still get some adsorption. So even though it's not as optimum as in the absence of the salts, but you can still remove it. So we were doing the adsorption. We also wanted, after taking the pollutant, can you recover? Because you don't want to prepare a material to then go to garbage again. So we were recycling it, and then we were using different solutions to recover the pollutant, the adsorbent. This is the EDS treatment, the EDS spectrum after the desorption. The metal is, with green tea, no copper, and then after the desorption you have no copper again. So all the copper can be removed out of the adsorbent. So let me just move on a little bit to the emerging pollutants. So can we use this with these new pollutants? The emerging pollutants, there is a lot of emphasis now with emerging pollutants. What is happening with all these pharmaceutical drugs, antibiotics, and things that are now populating our waste as our residual water, for example, triclosan, or with this wave of the hand sanitizer. Where is this hand sanitizer going? This hand sanitizer is going to the wastewater. So are we doing something about cleaning that? So we're trying to mimic this also to see if we can clean this type of pollutants using this technique. Then we want to do it like a systematic way using columns. We will also use columns, and then finally we did the chemical modification of the adsorbent. Now that we identify what are our special functional groups, can we overpopulate our surface with those active sites? That's also one of the goals that we're doing right now. So we are, first we target enrofloxacin, which is an antibiotic, and then as you can see here, the kinetics is really fast. So in less than an hour, I would say like 45 minutes, you get all the enrofloxacin, the antibiotic, gone. So it's just the UV absorbance of the solution after the adsorption, right? And then here we also have enrofloxacin adsorption at different pHs. Here, this one didn't work that well. We have chitosan, and then here is alginate beads. We have here also a pH 6, which is the highest adsorption. Here is the continuous flow experiment. It's a column experiment. We just packed a column with chamomile. We were able to remove up to, here is about 25 times 7, about 140 milliliters of water with a column of chamomile. That chamomile column had only 1.8 grams. So we clean all that. Of course, you saturate your column, and then here this drop is water. We flush water just to make sure that the copper didn't get stuck, on the gaps in the column. So you flush the water just to make sure that the copper is not precipitated. Otherwise, it would show you here a high copper amount. Sorry. So for the chemical modification, we were incorporating 3 different groups: sulfonation, we have carboxylation, and we have thiolation. So very simple reaction, cleavage, incorporation of the sulfonic acid. For the thiol, we just have an ester that had in the other end, it has a thiol group. And for carboxylation, we were using succinic acid, sorry. So as we can see here from the results, so the carboxylation definitely is increasing. The adsorbent prefers the carboxylation. This is the control, this is the no modification, and then that's for the carboxylation. Peppermint definitely prefers to get carboxylated to do the adsorption, so we are removing. So finally, I just wanted to close this saying that we're using these materials as a scaffold. we don't really want to oxidize, we don't really want to break the adsorbents. What we want to do is add things, because we're using that as a skeleton for the chemical modification. So right now we're working on the emerging pollutants. So we're right now doing penicillin, we're doing amoxicillin, which are the other antibiotics. So we're also trying to move ibuprofen, and then all the, most of the bisections, right? So that's our goal right now. Okay, so the references that we get done, and then that's the group. It's a very large group. Most of them are here with us. So thank you, all of them, all the students. Bright students are going to be also presenting posters later, and then thanks, of course, for the funding and for your attention.
Yeah, I believe we can take one question, at least at this time, if anybody does have a question. No questions? Okay. Oh, we got one here.
After removal of the metal, what you will do with the sludge, whatever you have, plant material, biomaterial?
Oh, we can recycle it. So right now what we did, for example, we did it up to 5 cycles. So you use your material, you adsorb, then you clean it with a smaller volume of co-solvent, take out the pollutant, and then you get your filter back. And then you can use in a second cycle, third cycle, up to 5 cycles. If you ask if the adsorption decreases, it decreases, but very little. What it happens is that you might deteriorate a little bit your material, but other than that is the removal. Is Tealeaf, so it doesn't really, it can get biodegraded, so it's biodegradable. So it's not, I think, since you are removing the pollutant, you are really not contaminating anything, because the pollutant is out of that, so you can dispose of that whenever you want. Thank you. Yeah.